Before we go on, I thought it would be useful to look at a practical example of linear approximation, one that you have perhaps seen before. And that is, we have a function from minus 1/2 to 1/2, and it has even symmetry. So any function with even symmetry on minus 1/2 to 1/2 can be approximated or built up. We'll deal with the approximation in just a moment using harmonic cosines. So this would look like this. X of t is equal to some DC term plus sum from k equals 1 to infinity alpha k square root of 2 cosine 2 pi kt. So basically what we're doing is, this is all based on the fact that we have a Fourier series, and if it's an even function, you could do a Fourier series expansion and get rid of all the sine terms because the sine would be odd. And also, this can be viewed, of course, as a basis expansion. So in this case, we'd have v0 is equal to 1, and v1 of t is equal to square root of 2 cosine 2 pi t, and so forth. And you could double check, but you'll find that vk vl is equal to 0 for k not equal to l. Actually, let me just write this differently. It's equal to 0 for k not equal to l, and 1 for k equal to l. So I say that, but probably the first question you should have in your mind is, okay, sure, I believe you, but what's the inner product? The inner product will be our standard inner product on a continuous signal. And so let's just define that here so we have it to reference later. X comma y is equal to the integral over the whole thing of x of t, y of t, dt. So there we are. So we can come up with the expansion coefficients for this little triangle function if we like. And we can do that by well, alpha 0 is just going to be 1 times the integral of our x of t dt, and let's see, what is that? So we're going from minus 1/2 to 1/2, so our base of our triangle is 1. The height is 1, so we can just note that that's 1/2. I'm not going to calculate all the rest for you, just in interest of time, but I'll set this up. So we would have x of t square root of 2 cosine 2 pi kt dt, where x of t is equal to 1 plus 2t, 1 minus 2t for, I didn't give myself much room, minus 1/2 to 0, and 0 to 1/2. Okay. So there we go, and we can actually do this integral. It's not too bad, and we would get 0 for k is even and k not equal to 0, and 2 square roots of 2 over pi squared k squared for k odd. Okay, so we can do some checks, if you like, just to make sure that math isn't letting us down at this point. And we can find the norm in both spaces. In time and in frequency, but we're going to talk about it here as the coefficient space, because really we're already, it does have frequencies, but you can see that if we chose a slightly different basis, it's just good to get used to talking about it in the more general terms when it's not always a frequency. Okay. That's equal to 2 times, because it's even, so let's just do half the integral, and this would be 1 minus t squared dt, and if we ran that out we would get not 1/2, but we'd get 1/3. Okay, if instead we did it in the coefficient space, we would have k equals 0 to infinity of alpha k squared. This is kind of crazy. Okay, so alpha k0 is 1/2 squared, or just 1/4. I'm sorry, alpha 0. Okay, there. Plus, when we square 2 square roots of pi, we get 8. Or 2 square roots of 2. And when we square pi squared, we get pi to the 4th. And now we have to sum up over all the odd terms. So how do we do that? Well, let's use k prime is equal to 0 to infinity. And for our k, we'll have 1 plus 2k prime. That gives us our odd values. It was squared before when we up above, but now we've squared that again, so now it's raised to the 4th power. So how do we do this? We use the formula for it's going to give us a really strange expansion, and I guess I'm just going to tell you what the answer is for right now. But this is equal to 1/4 plus 8 over pi to the 4th times pi to the 4th over 96. Those cancel. and 8 goes into 96 12 times. So 1/4 plus 1/12 is equal to 1/3. So I probably played fast and free enough with the mathematics that you're not fully convinced unless you go and figure out that sum by yourself. But if that's your thoughts on the matter, then go ahead and do that yourself. But I'm just going to keep going. So we can truncate this expansion that's the whole point of what we've been doing at k terms. So we would say xk, I'm going to put a capital K there and do my best, of t is equal to, we'll keep the dc term. If we truncated it at that point, there wouldn't be anything left. So alpha k square root of 2 cosine 2 pi kt. And let's go ahead and look at what these would look like. So this first one is what happens when capital K is equal to 3. I'm sorry, capital K is equal to 4. So this would be x4 of t. And here we have x6 of t, so k equals 6. And you can see that it's a little bit better. It started out looking pretty triangular-like with x of 4. And finally, here's what we have with 8 terms. So k equals 8. And it gets closer and closer. And you see where it's furthest off is right here at the boundaries, but it's starting to track that really closely. So we can compute the error for each of these explicitly. And essentially, that error is going to be the sum of all the terms that we didn't do using the linear approximation notes from before. We get alpha k squared, where alpha k from before is equal to 0 for k even and not equal to 0, and 2 over 2 pi squared k squared for k odd. Okay, so this tells us, well, we can see that the approximation is pretty good. And why is that? It's because this gets small quickly. As k increases. And so it's really quite common actually to have something that is a basis expansion that gets smaller if you have an infinite basis set as it gets larger, as you get larger in index. And there are some fundamental reasons for that, actually. But that's, I guess, a little bit further afield than we want to go to. But for now, there's just one good example of how this all works. So in the error, in fact, I'm going to put the error here as the last thing. The error for this one, x minus x4 squared, so error squared is going to be 1.9 times 10 to the minus 4th, and this is going to be e squared is 6.0 times 10 to the minus 5th, and this is e squared on this one is 2.6 times 10 to the minus 5th. So it's decreasing as we go. All right. That's it.